So I'm recording my screen already, and so this is where we left off, and I had to look actually on the video to see where I left off. So where I left off, the last question I did, we did this question here. That was the last one I did. So this involves something executing simple harmonic motion, like a mass attached to a spring going back and forth. And the question was about the energy. So we know that at the very ends, like right here, and this has potential energy, and that's equal to the work you had to do to compress it. That's potential energy of one half K A squared, where A is the maximum. It's called the amplitude, but it's actually the maximum value of X. And so as it goes back and forth, well, as it starts here, this is the total energy. But as it goes back and forth, it'll be at some different position, X, and it'll have some velocity. And the total energy now is going to be shown on the bottom here, 1/2 kx squared, where X is where it is, right over here, could be X plus 1/2 mv squared. So X and V are changing all the time, but they always add up to the same number, this number over here. Okay. And as the object goes to the center here, where X equals 0, it has no potential energy. It has lost all its energy, potential energy, but it has gained kinetic energy. So it starts off with 0 velocity here, or here. It loses potential energy, gains kinetic energy, and right here, when X equals 0, all the energy is kinetic energy. And you can see that here on the bottom. Right over here. That's the total energy at X equals 0. And again, by letting X equals 0, you see the total energy is 1/2 mv squared. All right, so let's do another problem here. What is the total energy of a mass spring system if the mass is 2 kilograms, the spring constant is 200, and the amplitude oscillation is 1/2, the amplitude is 3. So the total energy is, if I pull up the equation here, is 1/2 Ka squared. This is the total energy. So they're asking you, what is this? This is the total energy at any time. So the calculation is done over here. X is it's the amplitude this time, so it's 3. And so 1/2 K X squared, or A squared, it's 900 joules is the total energy. And what is the maximum velocity of that same spring system? In other words, when it oscillates back and forth, when it gets from here, this is the total energy, we just calculated it. What would be the total velocity when it gets here? How fast will it be going when it's at X equals 0? So let's take a look at that. So this is okay, this one here. So the maximum velocity involves letting 1/2 mv squared equals 1/2 kx squared. Okay, I'm sorry, equal 1/2 ka squared. So basically, by letting 1/2 mv squared, because it's lost all the potential energy. There's no x here, so 1/2 mv squared is equal to E total, which is 1/2 ka squared. And so if you do that, you get 30 joules per second. Let me do it just because 1/2 ka squared equals 1/2 mv squared. And we're searching for V here. All right. So, and this is the maximum velocity. The maximum velocity occurs right when X equals 0, and that's why this is true. So here the halves cancel off, and V is going to equal to the square root of K over M. So if you just put in K here, 200 divided by 2, this equals to 200 divided by 2 equals 100, so this should be like 10 meters per second. No, I forgot A, and you made a mistake here, guys. I forgot A completely. All right, so V equals square root of K over M. Yeah, forgot about the A times A, which comes out to, so there's a 3 squared over here, and now this comes out to 30 meters per second. Okay, this A is out of the square root, right? The square root is over here. The A is out. When I square it, I get K squared, I get K over M, but A squared. So A is 3, that's square it. This is 10 times 3 gives you 30 meters per second. Okay, let's see. A block with a mass m is attached to a spring with spring constant k. The block undergoes simple amount of motion. Where is the block located when its acceleration is a minimum? Because don't forget, everything is changing as the block goes back and forth. Its velocity is changing, the force acting on it is changing, and its acceleration is changing. So what do you think? I'll give you a hint, and then hopefully some people will answer. I'm going to take a look here if anybody's answering. Well, I'll give you a hint. The hint is this. A is equal to F divided by M. So A will be a minimum when F is a minimum. So the thing is oscillating back and forth. It's attached to the spring. When is the force a minimum? Or where? In fact, I'll give you a picture. Here's F. Here's F. Here's F. Here's F. Here's F. So when is the force a minimum? Well, as you saw in the picture, right here. Force is a minimum right here when x equals 0. And therefore the acceleration will be 0. Don't forget the acceleration is changing. This is not constant acceleration. So what we've been doing here, we've been looking at the mass-energy relationship for this. And I'd like to point out one more time that the velocity of this is changing. And it's maximum right over here. Okay, as you can see over here. The velocity is maximum when it's at x equals 0. So basically, if we set x equals 0 here, and we can therefore solve the equation that 1/2 mv squared, the maximum velocity, that maximum velocity equals 1/2 ka squared. So this is a connection. We're going to be using that pretty soon here. So let's do one problem just to calculate that. What is the maximum velocity, given this, m equals 1, attached to a spring of k equals 100, stretch point 1, what is the maximum velocity of the block? Now we did one like this with a little different numbers. Just let's do it again. First of all, let's see if you can do it. This is pretty easy calculations, guys. Turns out very easy. You don't need a calculator. Well, we are going to use this equation. Okay. In solving this equation, you can just solve it and do this, or you can just write the whole thing down. So 1/2 m, which is 1. V squared is what we're looking for. Equals 1/2 ka squared. K is 100. And the amplitude is 0.1. If you square that, you get 0.01. So now can you solve this? I see not too many people want the extra points that I give for per class participation. Right, this is a tough calculation. 1, because 100 times 0.01 is 1. So V squared equals 1. V, therefore, is going to equal to 1 meter per second, yes. Okay, so we're going to move on now, finish that part. So we're going to go back to derive some equations about the period of various things executing simple harmonic motion. So I'd like to bring back something we started this chapter with, is the fact that there's a connection between simple harmonic motion and uniform circular motion. And you can see the connection. They both have the same period. They both have the same radius. The radius here, we call it the radius here, but here we call it the amplitude. All right, this distance here is the amplitude, but those are the same things. So the amplitude is here is equal to the radius here. The period here is the same, and the period here. Now, what we're going to do is we're going to try to derive an equation for the period of this mass oscillating up and down. And basically, this also would be part of the lab today. What's the equation for the period of something oscillating in simple harmonic motion attached to a spring like we have here? Tough. It looks tough. But here it's not tough. What's the period for this object going around in a circle? Period is how much time for it to go around once. Well, that'll be pretty simple. The period should be distance divided by velocity, 2 pi r. This comes from the fact that the velocity is distance over time. if t is one period, this is 2 pi r, and t will be d, which is 2 pi r divided by v. This is pretty easy. And here, v basically is constant. So it's not like it changes all the time like over here. It just stays constant. So we're going to use this. Now, what I'm going to show you again is that for this situation that we just covered, there's a maximum velocity which occurs right at equilibrium. And it's given by that equation. We just discussed that. I want to show you that this maximum velocity, in a little film, I'm going to show you in a little film, that this maximum velocity is the same as this constant velocity. So let me show you that film here. Make this a little bigger. You see the velocity here changes, but look at it when it's at x equals 0. Those two velocities are the same. I'm going to stop him, hopefully the next time around. Let me do that. Right. Well, I got to move a little bit more. Right there, the two velocities are exactly the same. You can see these arrows are the same. So this velocity, the maximum velocity here is equal to the constant velocity here. Okay. So we're going to use that in the next slide here. So we would like to get an equation for the period in terms of the amplitude, k, and the mass, all these other things here. And so again, these two velocities are now the same. So the particle speed anywhere in the circle, the one that's going in the circle, is always equal to v equals 2 pi r over t, over the period. And so this v is going to be equal to the maximum v over here. We set this equal to 1/2 mv squared. This v is going to be v max, which means it's going to equal that. Okay, so I'm just going to put on this as the maximum velocity. We did this a couple of times already, but we didn't do what I'm going to do now. So v is equal to d over t, 2 pi a over t. T is the period. That's for this thing going in a circle. And here, for this thing going over here, v is equal to v max. So we are going to set this equal to that. And this we know also is from the last equation just had on the board over here, is km over a squared. V squared is km over a squared, right? Don't forget this comes from over here, solving for v. Okay, and you get that. You solve for v squared, you get that. And therefore, lo and behold, we can solve this equation for t, right? This equals that. Let's solve it for t. Well, first of all, the a's cancel. What does that tell you? That an object going in simple harmonic motion, that amplitude doesn't matter, the amplitude of the spring. Okay, so t squared is equal to 4 pi squared times m over k. Solve for t, you take the square root of both sides. Yeah. The square root of both sides, and you get, well, this is just 2 pi. Square root of m over k. I'll pull it out here. This is the, you've probably, I think, seen this a couple of times here and there, But where does it come from? Well, this is where it comes from. And this is why we have uniform circular motion to help us find that equation. So first of all, this tells you what? That in a spring, it's oscillating back and forth like, which slide was that in? Right over here. It's oscillating back and forth. The period is independent of the amplitude. Okay, I can drag this further up and the period will be the same. And basically, it's one of the things that you're going to do in the lab. You're going to verify that equation experimentally. So, but let's do a couple of problems now using it. So here's a problem where we have I'm going to move this so I can see who's answering. So what is the period of a mass spring system, like the one we just saw? Hey, by the way, a mass spring system also is this. You hang a weight here. This is the equilibrium line. We're going to pull it past here, and you let it go. And this is the period, the time for one oscillation. So what they're saying is this, if I pull it, if the amplitude is bigger, the time oscillation is still the same. That's what it's saying. Amplitude is not in that equation. Okay, let me go back. So what is the period of it? So this is the equation you got to use. Basically, use that equation to answer the question. So in this problem, this is going to be 64. This is going to be 64. And this is going to be 4. And both of these are perfect squares, so you know this is 2 divided by 8. But you got to multiply by this, and you get 1.6 seconds, this particular period. What if you want to know the frequency? Well, the frequency is related to the period. How? So you could find it that way. And these answers are not correct here, I see. Well, they're not, numerically they're correct, but this should be per second, the unit should be. In other words, 1 over seconds. Well, you can just do nothing but invert the answer you got here. The answer here was 1.6, so the answer is going to be here, it's going to be 1 over 1.6. Or you can use the equation right from scratch, invert the whole equation. All right, frequencies, instead of being 2 pi square root of m over k, frequency 1 over 2 pi square root of k over m. And you can do that from scratch here. So this is 8 divided by 4 is 2. But the answer would be 1 over 2 pi, and if you calculate that, you will find that it is this answer over here. All right, let's do another problem. What is the speed of a particle in circular motion of radius 2 meters with a period of 5 seconds? I'll give you a hint. Velocity is equal to distance over time. The period is 5. That means if t is equal to the period, d is equal to 2 pi r. Right, so E is the right answer for those of you who are answering. So using the same equation, well, we won't do this, but we'll just write it down. Using the same equation, velocity is equal to 2 pi r over the period. Now, I'm not going to put in the period because they give you the frequency here. So 2 pi r f, right? Frequency in the period inverses. And this comes out to be 75. Okay, number 24 here. Okay, I'm going to skip that for now. That one too. Okay, so we've done problems like this, so we don't need to do it again. So here is one little tricky problem. So again, we're going back to the thing oscillating back and forth. And we know that the energy is changing all the time, but it's equal to the total energy to begin with. But each energy, potential and kinetic, is changing as it goes back and forth. But the total energy, which is equal to that, stays the same. So for what value of x is the potential energy 1/2 the total energy? In other words, when it's going back and forth, where is it so that the potential energy is 1/2 total energy? I'm going to give you a little bit of hints before I come back here, and the hint is in the next slide. I'll come back to this slide in a minute. So in something that's oscillating back and forth, the total energy is the sum of potential plus kinetic. This is the potential. Both of these is changing. This is the kinetic. But the total stays the same. So what are they asking here? For what value of x is the potential energy, which is this. This is the potential energy. 1/2 of the total energy. This is the total energy. For what value of x is this 1/2 of this? Let's see if now, with that hint, can you do it? Actually, I can keep it in the other slide, and I'll come back here so you can look at the equation that you're going to need to use. For what value of x is this 1/2 of this? Okay. I mean, a lot of people would think that would be right in the middle. No, it doesn't turn out to be that. Surprisingly. Okay, so all right, so basically what we're asking you is solve for x. For what value of x is 1/2 kx squared, which is the potential energy, equals half the total energy. The other half obviously would be kinetic. So you can see the halves cancel here. And kx squared, k's cancel. So x squared equals 1/2 a 1/2 a squared. What's x? Again, I'll give you one more glance before we go to the answer. .7a. So the answer would be D. I see nobody got it right, so we have to do another problem, right? It's a very similar problem. Maybe you get one on the next test like this with different values, different percentages here. So how about this one here? For what value of x is the energy 2/3 kinetic and 1/3 potential? Again, this is the equation here. This is the total energy. And you want to know for what value of x is this equal to 1/3 of that. One halves cancel, k's cancel. So x squared equals a squared divided by 3. No, this is, don't forget, you got to take the square root of the 3 here. All right. Because I see somebody put down A. That's a good shot, but don't forget you forgot to take the square root. So don't forget you take the square root of the things on the right. Square root of A squared is A, but you got to divide it by the square root of 3. Ah, that's better there, Alexander. Yeah, so it turns out that it's going to be about, it's 0.59, so the closest answer is here. Of course, a follow-up question, we're not going to do it. Maybe I'll save it for a test. How about the other way around? 2/3 potential, 1/3 kinetic. Instead of 2/3 kinetic, 1/3 potential. Yeah, maybe I'll save that for the test. Okay, so this is the one we just did. I'm going to do it again. So now we're going to go up to the simple pendulum. Simple pendulum consists of a mass at the end of a lightweight cord, in other words, a string that basically has no mass. We assume that it has no mass and also does not stretch. So basically, in the pendulum, first of all, we're going to have a little bit later conservation of energy. That if you take a pendulum, right, and you stretch it, it has now gravitational potential energy, MGH. Okay, if you let it go, it comes down, swings like this, and when the ball is at the bottom, this is the simple pendulum, it's a mass, this mass is at the bottom, all that energy is changed into kinetic energy. So somewhere in between, there is a sum of potential plus kinetic. The height gets smaller, the velocity gets bigger, so the total energy stays the same. But before we do any problems using that, what I like to do is, you did a pendulum in the very first lab, if you remember. You verified an equation for the period of a pendulum. And basically, we're going to derive that equation right now, then use it a couple of times. Maybe I should just demonstrate, first of all, a pendulum here. I think I have one. I think I have one over here. What I'm going to show you is that the pendulum has something to do, the period of a pendulum has something to do with the period of this mass attached to a spring. So what I'm going to do is I'm going to push the mass and compress it, and the result of that, that's the same as stretching the pendulum. So right now, the total energy of both of these is potential energy. No kinetic energy right now. But what happens when I let it go? Look at what happens to the kinetic potential and the total. The total is red, it stays constant, but the kinetic plus potential change. When one gets bigger, the other one's smaller. All potential, all kinetic, all potential, all kinetic. Okay? For both of these, they're exactly the same. Look at the force here. The force here is varying. It's big, it's zero, it's big, it's zero, it's big, it's zero. Look at one of the forces here. The only force that's acting on this, well, two forces, is the weight is down, and there's a force over here of the string up. But there's a force over here which is varying just like this one here. What is that force? Well, that's what we're going to find out. First of all, we want to make an approximation, what's called a small angle approximation. And small angle being, let's say, anything that's around 10 degrees or less. I want to make an approximation of the following approximation I'm going to show you here. But to do this, theta must be in radians, okay? We have to convert this to radians. And here's the thing. For small angles, the sine of the angle in radians equals the angle in radians, or the sine of the angle in degrees equals the angle in radians, approximately. Let's see if that's true. And basically for the same reason, the cosine equals 1. And the tangent, which is sine over cosine, that would be theta divided by 1, is also the tangent of any small angle is approximately equal to the angle in radians. So let's do it for 10 degrees. Now 10 degrees is 0.157 radians. Now if I find the sine of 10 degrees, I find that the sine of 10 degrees is 0.156, almost the same. And the cosine is almost 1. Well, let's make the angle even smaller. How about 5 degrees? Now 5 degrees, if you convert that to radians, is 0.0872 radians. Let's see what the sine of 5 degrees is. Almost identical. Let's see what the cosine is. Almost 1. Even closer than 1. So you can see we can make this approximation that the sine of any angle, if the angle is small, the sine of that angle is approximately equal to the angle in radians. All right. So let's see where that comes in. So here we're going to have a pendulum. And as we saw, the pendulum was swinging. There were two forces acting on it. This was the string, and this was the force of gravity. What we're going to do now is we're going to resolve those forces into components, and we're going to draw our y-axis tilted, like in the inclined plane, you remember? This will be the x-axis. This will be the y-axis. Now, there's a reason for that. So basically, if the x-axis is this way, and the y-axis is that way, let's resolve this vector here, which is mg, into components. So I'm going to replace that vector here, mg, with these two components. I'm going to put this one over here. So now what I can do, I'm going to be able to just remove that one, and I can do it over here. But before I do that, let's put in a couple of angles. So this angle here is equal to theta, and this angle here is also equal to theta. You can see that these are the same angles. So if this is mg, this is side adjacent to theta, that's this one here. That's this red here. This is the side adjacent to theta, right? That's the same as here. That's equal to mg cosine theta. And this side here, that's the same as this, is going to be mg sine of theta. And I have that written over here. So this is mg cosine theta. This is mg sine theta. And this basically is this restoring force. It's mg sine of theta. Okay? Because as the object swings, these two forces don't do any work. This is the only one that does any work. And you saw that in the simulation that I had. Let me put that up one more time. So the force that matters is this one here, right over here. And this is sort of like this. It's a force that's varying, just as this one is varying. So in simple harmonic motion, there is a restoring force, a force that always brings it back to equilibrium. And that's this force here, equilibrium being right in the bottom here. It's trying to bring back the object to the bottom, the ball, the mass here. And it's the restoring force. So that force, as we saw, is equal to Well, it's negative minus mg sine of theta. So now we're going to go Fx, right, the tangential force, which is proportionate to sine of theta, not to theta itself. Okay, this is theta here, and this is theta. It's proportional to the sine of theta, but theta, sine of theta is equal to theta for small angles. So do we have simple harmonic motion? If so, what does it look like? Let's go to the next slide. So we're going to make that approximation, the small angle approximation, that the sine of theta is equal to the theta, small angle sine of theta is approximately equal to theta. And what that means is that we look at, remember, circular motion, we said that theta in radians is related to the arc length here, to this distance, and to the radius, which we call L. Basically, the ratio, remember, was theta was equal to, in the circle, was delta S over R. In this case, instead of R, we have this distance. I'm sorry, we have L here. L is R, and delta S is just this distance. I'm going to call it X. Okay, and this is L. So we're going to put in for theta X over L. Okay, X over L, or theta divided equals X divided by L. And so when we put that in here, we get this equation. F is equal to minus mg theta. Now, remember, in simple harmonic motion for the spring, F was equal to minus kx. So that was the restoring force. Okay, so basically this looks very similar. Instead of having a k here, we have an mg. Instead of an x, we have theta, which is like the same thing as x. It's something that's changing. You see, it's changing, like x was changing in simple harmonic motion. So we're going to play a trick here. We're going to take the equation that we already have for simple harmonic motion, all right? And we're going to put in this for k into that equation. If we look at this, k is equal to mg over L, okay? We compare this to this, put in for theta x over L, right? We're putting that in for theta. So what this looks like is mg over L. Just move the L over here. And basically it looks like this. It looks like the other equation, except for k, we have, instead of k, we have mg over L. Okay, so we're going to assume k is equal to mg over L, and we're going to put it into the equation that we already have for the spring. We're going to put that in there. Okay, and the reason for that is this sort of seems to be the same thing when we made that approximation. And so what happens when you put that in? Well, put in for k mg over L, the m's cancel first of all, and this becomes L over G for the period. For the frequency, turn this upside down for G over L. And you remember, for the period of something oscillating on a string, the mass of the thing that's oscillating doesn't matter. Okay? And that's because it canceled out over here. Neat trick, no? All right, so basically enough tricks. Let's do a couple of problems for the pendulum. Let me find my problems here in a second. Let me just, I can't copy that equation, I don't think. I'll have to write it, yeah. Let me write that equation. T is, for a pendulum, the period of a pendulum is 2 pi. Hold on, let me just look here. Okay. 2 pi squared of L over G. And you verify, remember you verified this equation in the very first lab we did here. So let's do a conceptual problem, a question first. If the same pendulum were set in the moon, what would be the difference here? Same pendulum, same length, but what would be the difference in that equation? G is different. G on the moon is smaller than G on Earth. Now G on Earth we know is 9.8. G on the moon is 1.67. So what would be the period of a pendulum in the moon if you compare to on Earth? Would it be less than on Earth? T is the pendulum period on Earth. More or still the same? Well, obviously this equation makes the denominator smaller, which will make what? The period bigger. Okay. So let's do a practice problem here. We don't need that, okay. I'm going to skip these couple of problems here. I want to get to the pendulum problems, and they're, I think, way down here. So say we have a pendulum. They're doing the frequency, right? So they ask for the frequency, but we can calculate the frequency. Let's see if we can answer this question. So don't forget the equation we had for a period there, you could turn it upside down for the frequencies. The frequency is going to be inverse of the period. So it'll be 1 over 2 pi square root of G over L. It turns out, yes, B is the correct answer. Okay, so period is 2 pi square root of L over G. This is 1 inverse of that. 10 divided by 2 is 5, square root of 5 times 1 over 2 pi gives you B is the right answer. Now, there was a problem I skipped. I think I actually want to do that. No, the problem, these are, no. Okay, so that problem must be still coming up. So let's, what is the period of a pendulum with a length of 2 meters near the surface of the Earth? This is not multiple choice, so let's do this one here. So this is the equation you're going to use. So it'll be 2 pi, 2 times 3.14 square root of 2 over 9.8. And it is, yes, it is 2.81. Okay. Say we want to use, we want to build a clock, a grandfather clock, so that the period as it goes back and forth is 1 second. What length should we make it? So this is one for you to try. Well, so basically using this equation, but you're solving for L. So how do you solve this equation for L? What do you got to do to both sides? You got to square both sides. So you square the left side, you get t squared equals 4 pi squared. No, 4 pi squared is approximately equal to 40 times L over 9.8. And this is equal to 1, by the way, right? 1 second. So the question is to solve for this. L is going to equal to 9.8 divided by approximately 40. It's 39.4. I just rounded off to 40. And this comes out to be a few more people want to give it a try. Yeah, about a quarter of a meter. Okay, 0.25 meters or 25 centimeters. Okay, one more problem. So an object mass m attached to a horizontal spring. So this goes back to the spring equation, a horizontal spring. So the period is given by that equation, and it undergoes a period with a period of t naught. We're going to call it t naught. Now, what if you, don't forget the period here depends on the mass. It's not like the pendulum. It depends on the mass. What if you repeated the experiment with a mass of 4m instead of m? What would this new period be, let's call it t prime, compared to the old period? Would it be, which of these choices would it be? Well, can you replace in this equation m with 4m? Oops, 4m. Let me write it backwards, I guess. This is very easy because the square root of 4, you got to take the square root to figure out what the period is. So what would be the right answer? Well, what's the square root of 4? I think it's 2. So you get 2 times 2 pi square root of m over k, because the 4 came out already, right? There's the 4. But what is this? This is the original T naught, okay? So it'll be 2 times that. If you increase the mass by 4, the period will be 2 times bigger. So the answer is A. Okay. I see that many people didn't get that, so you understand this now? All right, you put a 4 here, you get 4m. Take out the 2, and what remains is that, but that is the original mass here, not the without the 4m, the original mass, and that was the original period that remains here. All right, so one last example. Something you didn't expect to find simple harmonic motion in, and that would be the whole Earth itself. Now, we talked about force of gravity, that as you go away from the Earth, the force of gravity due to the Earth drops off as 1 over distance squared. What does that mean? That means that if you double the distance, the force of gravity is 1/4. You triple the distance, you bring an object over here, it becomes 1/9. So, but what happens if you actually come closer to Earth, then you go inside the Earth? Say you go inside the Earth. Say there's a hole in the Earth. So here you are. You go inside the Earth. Well, it turns out, which I'll show you why in a minute, that the force of gravity inside the Earth drops off as 1 over distance, but not 1 over distance squared. And again, that means as you go toward the center of the Earth, the force gets lessened as uniformly, and it's 0 right in the middle. So, what if the Earth was hollow? Okay, in other words, there was a hole in there, you could jump in. If you could jump in, here you are jumping in. There's a force pulling you to the center, but that force is getting smaller and smaller and smaller and smaller and smaller, and it's 0 here. You can see it over here. The force gets smaller and smaller and smaller, and at the center, it's 0. But if you jump in, by the time you get here, your velocity is increasing. By the time you get here, you're going very fast. But now as you go through the center, that force is now up. And you slow down, slow down, slow down, and you eventually come to a stop. Is this familiar? The force decreases as displacement, as a function of displacement. The displacement here being r, the radius, the distance you are from the center. F is equal to k, not x, but r, but it's also the same. So let's take a look. What happens? Well, before we do that, let's watch a little film. Is that the one I want to watch? Let me just see. Yeah. We can do away with this film. Let's watch a little film here.
You ever wondered what would happen if you dug a hole from one side of the Earth, through the center, out the other side, and then jumped in? Before we show you, a few disclaimers. If there was any air in the hole, air resistance would slow me down. So let's ignore that. Earth's molten core is 11,000 degrees Fahrenheit. On the way past, you'd simply be vaporized. So let's ignore that too. We would also have to ignore Earth's spin, which would make me ricochet from side to side down the hole. And please don't try this experiment on the actual Earth. All right, here we go. I fall, gaining speed as Earth's mass pulls me towards the center. 14 minutes into my fall, halfway to the center, and I've accelerated to more than 15,000 miles an hour. Here, there's only half the force of gravity than on the surface. So I'm still gaining speed, but at a slower rate than when I first jumped in. 21 minutes into my fall, and I'm at the center of the earth, going my fastest, about 18,000 miles an hour. As I pass the center, gravity now works against me, slowing me down. And by the time I make it halfway between the core and the other side of the earth, I'm back down to about 15,000 miles an hour. It'll take only 42 minutes to make the entire trip to the other side, at which point I'll slow to a full stop. Just like when I started, all of Earth's mass will pull me back towards the core. Unless somebody catches me, I'll fall down the hole again and yo-yo back and forth forever. Thank you.
No problem.
Okay, so let's take a look at how it. So it looks like this is simple harmonic motion, but what's the period? How you saw that it takes 42 minutes? Let's see. That will be half a period. How does that come about? What is it? 42 minutes. Again, as you go in there, this force is getting smaller as x. In this case, we're going to use r as g gets smaller and smaller. So the g is that's pulling you down. The acceleration basically is the g on the surface times r, which is the how far you are down from the center. Like over here, you're this far r divided by the radius of the Earth. So g is changing. Your acceleration is changing from F equals ma. Now, if we look at F equals mg and put in for g this over here, this whole thing here, put it for g over here, and this is what I did over here, I get something that looks like this. This looks very similar to F equals kx. Instead of x, we have r. Instead of k, we have mg over r. So we're going to put that in here in this equation, because this is the period for a spring. We're going to put this in for k. All right? So we're going to put in for k that. What's going to happen here? Well, the masses are going to cancel off, and this r, radius of the Earth, is going to go up to the numerator, and we get this equation. The period, it means the time for the fall to go up and down, is going to equal to 2 pi square root of the radius of the Earth divided by g on Earth's surface. And that, if you put in the numbers, you get 84 minutes. Guess where you've seen that before? Where you've seen that before, you've seen it in orbital motion. That something in orbit around the Earth takes 84 minutes to go around once. So this is basically something orbiting the Earth, satellites orbiting the Earth, near the Earth's surface, take 84 minutes to go around once. If this was true, you can actually jump in and come back up, then that would take 84 minutes also. Go up and down. You saw that in the film. I could show you one more film to finish this class. It's similar. This is the one we just saw. I think I have another one here. Somewhere. Oh, maybe I don't have it. There was another one film that you can look on that, unless I have it over here. No, I guess I don't have it. Well, okay, so we're going to finish the class on this topic. And we're still not finished with chapter 13. We're going to continue a little bit more next time and then go on to 14. But let me talk about the lab today. So the lab is on simple harmonic motion, and we're using the simulation for a spring over here, which I think I already showed you how that works more or less. but if not, I'm going to show you again. So in this case, you hang a weight in the spring, and basically you, well, first of all, you look at what's the unstretched length of the spring over here. And then you're going to take a ruler, and what we want to do is we want to hang something and want to measure how much the stretch is. We're going to put it up. Let me start again here. Okay, so we have a movable line from where we were. The displacement that we have, we can measure all these things with a ruler. Okay, so you're going to basically, first of all, measure the spring constant by hanging a known weight, like I just did here, and measuring the stretch of the spring. And then you're going to follow directions, as I have here. I'm going to show you the lab write-up. So what we're going to do is we're going to try to verify this equation here by making a couple of graphs. Okay, first of all, we need to do what I just did. So this first part, you do what I just did. You basically hang different weights and look at how much stretch there was. And then you can calculate K from looking at this equation. And then you're going to hang in, again, different masses and measure the period. It tells you here to do it 3 times. You don't have to do it 3 times. Just do it once. You can measure the period. And to measure the period, you need to use a stopwatch, which is over here. And you can sort of set this up so that when you start this, the stopwatch will start. Okay. Make sure you put the damping down to 0 here. So I stretch it a certain length, measure the period. Okay. And if you make a graph, if you were to make a graph, you will find out you don't get a straight line. You don't get a straight line. So you have to, and why don't you get a straight line? Well, you can see the relationship between the mass and the period is not linear. It's not like a straight line, there's a square root here. So basically what you're going to do is, if you square that equation, you get that. So now you're going to make a graph of t squared. After you measure all the t's originally, you're going to square all the numbers here. So for example, let's say you were to get a period of 0.2. Well, I can write here. I just remembered of 0.2 here, but I can write somewhere else. You're going to square that number to 0.04, etc. All of these, you will square them. And then you will make a graph of the period versus m, and the slope of that graph, right? You're going to make a graph of t squared versus m. The slope of the graph should be 4 pi squared over k. So when you calculate the slope, you should be able to find what k is, because the slope of that graph, and I think I have more information on that over here. right? So this won't give you a straight line if you make a graph of t versus m. So you will need to actually square all these equations, square all of these periods, and then make a graph of t squared versus m. And when you make a graph of t squared versus m, you should get a straight line, hopefully. And that slope of that straight line, again, you find the slope by rise divided by run. This is kind of sloppy here. Delta y over delta x. And t squared equals 4 pi squared over m. That means the slope that you find is 4 pi squared over k. 4 pi squared over k. Because this is multiplied by m. So this will be the slope. So if you find the slope, let's say I'm going to just make a number up. Let's say the slope turns out to be 10. It's not 10, but let's make believe. So what you're going to do, you're going to let this equal 10. 4 pi squared over k equal 10. And then you will solve this equation for k. Okay. And then you're going to compare it to the k you found when you hung the weight. When you hung the weight, when you hung the weight over here, when you stretched the distance x, kx is equal to mg, which is 100 times 9.8. Let me also show you one last thing. To do that, I have to actually go into the lab folder. So let me do that while I'm still sharing my screen. So this is the lab, we're doing lab number 10. So I'd like you to actually do a good job because most of the graphs you guys made were not that good. I sort of let things slide, but this is what a graph should look like. This is a graph using Excel. And basically there's directions. I mean, it takes you 10 minutes to do that. Once you have your data, for example, in the pendulum lab that you guys did, this was the data that we had for the length of the pendulum versus the period. And this little tutorial here, it's a one page tutorial, maybe 2 pages, I already forget, will tell you how to go from here to here in 5 minutes to get a graph that looks like this. All right. So here you have the link to the and you have some description of how it goes. Now I'm going to, this last part where I talked about the lab, it's part of the main recording that I did, which I'm going to stop right now. But I will copy that very last part related to the lab and paste it in here as soon as the lab is processed, as soon as the video is processed. Okay, so let me go back to this. Stop recording.